Hello everyone. Welcome to another lecture on the lecture series of control system. Today we'll be discussing about the transfer functions. So transfer function is an important terminology. I think this will be the most heard or most used terminology it will be or it is in the control system lecture. So you will be also using this term quite frequently when you get well versed with the mm, control system paradigm. So let's understand what is a transfer function. So if you have watched my previous lecture on uh, closed loop and open loop system, in the towards the end I had introduced the transfer function. So I will be elaborating it a little bit more right now. So transfer function is nothing but the uh, equation like the set, nothing but a black box kind of thing. We can say like now I am throwing out another huge term, black box. So just imagine this is a box or this is a system, just some system. So we don't know what is it. It just when you put something like so if you give input as 5, okay, it gives output as, just imagine, it gives output some 12. Okay. So what can you deduce from the system? So the system can be like if my this is my y output and this is my input u. So I can take the my y is equal to uh, 2 into u plus 2, isn't it? But I can't guarantee it, right? Y can also be 2, y is equal to some uh, like 2.4 into u directly, or y can be 3u minus 3. So it can be anything unless I'm sure about it. So what I will do, I'll put another input. Let's assume it's the u is equal to 10. Then what happens? Now my output is 24. So out of these three expressions, I can get certainly, although now also I cannot guarantee, but there is a much chance of this expression. Like there can be other expressions as well, so which do satisfy this relationship. So just imagine now my y is 2.4 into u. Okay. So what this relationship, like the relationship between output and the input, is called a transfer function. So it's nothing simple like how my output changes with different value of control, like the input. So if I give some input, how my input is changed into the output value that is transcribed by the system, like the transfer function. Beg my pardon. So as an control engineer, so let's take an example, like a classical example of from aerospace point of view. So is a simple aeroplane. Okay, this is a fixed wing aeroplane. This is a classical fixed wing aeroplane. So fixed wing because it's the wings are fixed. There are only one rotor, like the one propeller. This so and like this propeller when it rotates in some direction, it produces thrust so that the vehicle can move in forward direction. These are like for non-aerospace background people. Aerospace background people will be well versed with the terms like ailerons, flaps, rudder, elevator, or fuselage, propeller. So, just a brief introduction to the non-aerospace background people. Ailerons are the like the control surface which help in moving the like if I take this as some x direction, this as y direction, and the downward as the z direction. So aileron helps in the rotating the flights in this direction. So I have another figure. I think I should mention it here only. So 1 second. Yeah, maybe I'll just put it here and put this figure here. Okay. So what aileron does, I look at my aileron. Aileron at the control surface which used in the roll. So I'll just draw some. This suppose this is x axis. This is y axis. So according to the convention, and this will be downward will be the z axis. Okay, it doesn't matter. So aileron will help in the roll. So what roll is? Roll is the rotation about x-axis, rotation about x, and yaw is the rotation about z, and pitch is the rotation about y. So when my aileron, like these are the flaps kind of things, so when it will go up or down, my vehicle will be tilting like this or like this. Okay, so for the movement this is used, and similarly when this rudder, this thing goes this direction or this direction, accordingly my whole vehicle, it's like it yaws, or like it rotates about this z axis, like if I am, this is the downward direction z, so it will be rotating like this. And uh, the elevators, they help in pitching, like it's if the vehicle will be going up or down, so uh, like that. So there are so many control surfaces, like here only in the diagram itself. One is the propeller, one is the aileron, one is the uh, sorry elevator, and another is the rudder. And there are many other control inputs to the fixed wing vehicle. So just take one schematic diagram. I know I'm very bad at drawing, so please bear with me in that. So if this will be my fixed wing helicopter, sorry, fixed wing, this the propeller, and this this is my mm, fixed wing plane. So here the ailerons are there, here the elevators are there, and here the rudder is there, and this is the propeller. So what happens is my control input I can specify as the change in the propeller, change in aileron, change in elevator, or change in rudder, or some external parameters, like if the wind velocity is different, then my vehicle will also be performing differently, like that can also be a uh, some other inputs are also there, some wind velocity, and also the air density, like all these parameters, like my performance of the flight will depend on these things. So, and my outputs will be like whatever output I want, like some velocity, uh, x coordinate, or maybe y coordinate, or the height, or anything else. Like suppose I'm assuming there are n inputs and there are m outputs. Okay, so when I, like, this is a very complicated system. Like the uh, aeroplane, any flight fixed wing vehicle is a very good, very complicated system and non-linear system as well. So let us analyze that when we talk about the transfer function, let us take one control input. Suppose I am taking the change in elevator, and I must say this is the change in this angle, change in uh, aileron angle, elevator angle, and the rudder angle. So just imagine I am using, I am changing my elevator angle, something like it used to be something, and now it's some, and how my height is changed. I want to get this feel like the remaining things are constant in the input. I just changed my elevator angle. Definitely, this elevator change in elevator angle will be like will uh, sorry. This change in elevator angle will change some x, y, height, velocity. Everything will be changed. But I want how much height change has happened. So if I take my u as delta e and uh, y, my output is the height. So the I can say the transfer function, it, which is the just is a input output uh, uh, like description like description. So how my in a like how the given input u uh, delta e has affected the height. So I can say that my system, the g of the is equal to h of s, like the Laplace transformation divided by delta e of s, like the Laplace domain transformation. So this is likely to be a very complicated relationship in between them. So I can say it's between delta e and y. Okay, sorry, height. Okay, so this is a complicated, but you get the feel, right? Like what is my transfer function? Given input, how my output is changed. That's like the description is called the transfer function. So technically, like the definition we can write is this uh, transfer function. I'm just using the short notation of an LTI system is defined as the Laplace transformation, Laplace transform of the output over the input. Here is an important term, assuming all the initial conditions to be zero. So here are some important terminology, like important factors you need to remember. It's for an LTI system, and we assume all the initial condition to be zero. Okay. So in general, LTI systems transfer function or LTI system is simple. General. This video will be a little bit long and little mathematical expression will be there, but bear with me. It's a very interesting uh, mathematical expressions. You will understand why the things are happening. Linear ODE. So ODE is the ordinary differential equation. So what it says is, suppose my system behavior is like a linear ordinary linear ODE, which is an dy of t by dt n plus a of n minus 1 n minus 1 y of t by dt n minus 1. So like that, a1 dy of t by dt plus a0 y of t is equal to bn. So the output derivative, so the input derivative u of t by dt of n plus b of n minus 1 d n minus 1 u of t by d to the power n minus 1, like that, b1 du of t by dt plus b0 u of t. So if we assume all these terms, this an minus 1, a1, a0, bm, bn minus 1, b1, all these are constants. I'll choose another color. These all, everything are constants. So this is simply a linear ordinary differential equation. So to solve this equation, it will take a lot of time and lot of hard work. Like it is very complicated to solve. There to rescue how to solve it. Like what we want. What we want is how my output changes. Sorry, how my output changes with the input. Like this is all we want. Like if we get some expression here, then our life is easier, simpler. Like we get, then we can predict like whatever input u we give, what will be the output y. So, and for the transfer function definition, like the Laplace of this yt, y of s by u of s, that this all we want. So to the problem is how to solve this expression. This is a very huge expression, and to solve it, it in simple mathematical expression, it's very complicated. So to rescue this, there comes the Laplace transform. So what Laplace transform does, this odd like to solve this, definitely we will be needing the integrations, because there are the derivative expressions. These are the derivative expressions. To solve them, you need integration and all, which is very complicated. That's why to rescue you, there comes the Laplace transform. So what Laplace transformation will do? It will convert this ODE, the differential equation, into algebraic expressions, like the sum, like the plus minus, just some algebraic manipulation, and you will be getting the answer. So Laplace transform's beauty lies in its solution approach. It converts a differential ODE into algebraic. How does it do? In like, I won't be discussing much about the Laplace transformation in this lecture, but I will just brief about what are the important like Laplace transforms you will be needing in this lecture. So one Laplace transform is like simple. Just imagine that you have some f of t, uh, and its Laplace transformation is L of f of t is f of s. The just note that this is a small lower cap f, and this is a uppercase F, like capital F, whatever you can call it. So if I multiply a constant with f of t, its Laplace transformation, a of f of t will be a into f of s. If I like sum to like a f of t plus b g of t, then the Laplace will be a of f of t plus b of g of t. This will be a of capital F of s plus b of capital G of s. So, and another, the most important one which you will require is the derivative. If nth derivative of f of t divided by t to the power n, it the Laplace transformation of this will be f of t by d to the power n. This will be s to the power n, here the capital f of s minus s to the power n minus 1, small f of 0 minus s to the power n minus 2 d by dt of f of t at 0, f of 0, and like that till minus dn minus 1 dn minus 1 of f of 0. So as you like, for our case, like for the Laplace transform definition which we had mentioned, just look at this term, assuming all the initial condition to be 0. So if we assume all the initial conditions to be 0, then simply this will be 0, this will be 0, this will be 0. So what we end up with? It's s to the power n capital F of s. So we can write for our purpose, Laplace transformation of d n f of t by dt to the power n will be s to the power n f of s. Just remember this. This will be a life-saving for you expression. So now coming back to our expression, I'll just copy this. Okay. So what will be the transfer, like the Laplace transform of this? Yes, you can calculate by yourself. I am just writing it down. So this will be simply s to the power n capital Y of s plus a to the power n minus 1 s to the power n minus 1 capital Y of s up to a1 s y of s plus a0 y of s is equal to bm into s to the power m u of s plus b of n minus 1 s to the power n minus 1 u of s up to b1 s u of s plus b0 u of s. Okay, so ultimately if I take out the ys common in the left hand side and the u of s in the right hand side, I'll get y of s whole into e to the power n an s to the power n a of n minus 1 s to the power n minus 1, sorry, minus 1 up to a0 is equal to u of s to the power m plus, sorry, bn s to the power n plus bn m minus 1 s to the power n minus 1 to b0. So what will be my transfer function? Is equal to y of s, the Laplace transformation of this y of t, and divided by Laplace transformation of u of t. So y of s by u of s is equal to bm s to the power m plus b n minus 1 s to the power n minus 1 up to b0 divided by an s to the power n plus a n minus 1 s to the power n minus 1 up to a0. This is the expression for Laplace transform. So a common transfer function for LTI system. Okay, this is very important. You don't need to remember all this because as you know the concepts right now, you can derive it easily. And one term is in general, not a hard and fast rule. N is greater than or equal to m, which is called proper transfer function. And if n is strictly greater than m, then it's called strictly proper transfer function. So why we need strictly or why in general, that concept can be explained in another lecture. So, so today what we have learned is like what is a transfer function and the aerospace aspect of it, like uh, how by changing the ailerons we can change the roll, which is the about x-axis, and this direction. By changing the elevator we can change the pitch of the, like the vehicle will be going up or down, like this movement. And by changing the rudder we can change the yaw, which is about the z-axis. Okay, and we explained what is the transfer function, and we derived, like for a LTI system, what is the generalized transfer function. So the property we can say about the transfer function is like it relates the output to the input. And the beauty about it is like why we want a transfer function is, so if you want to predict what is the output, like what is the response to a step input, which is step input, which is simply like this in time domain. So you want like how some sinusoidal, if I give input as a sinusoidal input, sinusoidal input, which is like this in t. So how my system will behave? So simply my y of s will be the transfer function into u of s. So just the transfer, like the uh, Laplace transform of the sine wave, multiply with the transfer function, you will get the y of s. Do the inverse Laplace transformation, you'll get the response. So that's why we need the transfer function. So that's all for today's lecture. In the next lecture, we'll be taking one example, and some MATLAB code. Uh, we'll be taking the example of the classic spring mass damper, spring mass damper system. For the electrical guys who are watching this video, spring mass damper system can be equivalently say what in electrical domain a simple RLC circuit does. So till that video, uh, goodbye. We'll meet in the next lecture. Thank you.